We will now discuss the simple moving average. The simple moving average, SMA, is a powerful forecasting method, particularly effective when demand neither grows nor declines rapidly, and when seasonality isn't a factor. By averaging a fixed number of past periods, the SMA helps eliminate some of the inherent random fluctuation from the data, resulting in a smoothed trend line that better represents the underlying pattern. One crucial aspect of SMA is the selection of the period length. A longer period length offers more smoothing, thereby minimizing the impact of short-term fluctuations, but might be slow to react to real trend changes. Conversely, a shorter period length enables the SMA to react more quickly to trends, making it more sensitive to recent changes, but potentially leading to a noisier signal. In essence, the choice of period length in SMA involves a trade-off between responsiveness and stability. The simple moving average formula, represented as F sub t, equals the sum of A sub t minus 1 plus A sub t minus 2 plus A sub t minus 3, and so on, up to A sub t minus n, all divided by n, is a straightforward and practical tool for statistical data analysis. In this formula, F sub t stands for the forecast for the next period t. The number n represents the number of past periods that are averaged. A sub t minus 1 denotes the actual occurrence in the previous period, while A sub t minus 2, A sub t minus 3, and A sub t minus n symbolize the actual occurrences 2 periods ago, 3 periods ago, and so on, up to n periods ago. By averaging these actual occurrences, the SMA formula helps smooth out data fluctuations and provides a clearer view of the data trend over the specified period. In the context of the simple moving average, SMA, we will consider two examples, a 3 weeks SMA and a 9 weeks SMA. For the 3 weeks SMA, we use the formula F sub t equals the sum of A sub t minus 1 plus A sub t minus 2 plus A sub t minus 3, all divided by 3, where Ft represents the forecast for the next period, and A sub t minus 1, A sub t minus 2, and A sub t minus 3 represent the actual occurrences for the previous 3 weeks. In contrast, for the 9-week SMA, we expand the range of periods being averaged using the formula F sub t equals the sum of A sub t minus 1 through to A sub t minus 9, all divided by 9, where values from the previous 9 weeks are averaged to produce the forecast for the next period. These methods allow us to calculate different SMAs based on the number of weeks being considered, effectively smoothing out the data over these respective time frames. The weighted moving average, WMA, is a modified version of the simple moving average, SMA, that assigns different weightings to data from different periods. Unlike the SMA, which gives equal weight to all periods, the WMA provides a more flexible approach, allowing for unequal weighting of prior time periods based on their relevance. The WMA formula is represented as F sub t equals W sub 1 times A sub t minus 1 plus W sub 2 times A sub t minus 2 plus W sub 3 times A sub t minus 3 plus up to W sub n times A sub t minus n, where the weight W sub 1, W sub 2, W sub 3 through to W sub n sum up to 1. Selecting this weight usually involves experience, trial and error, and the understanding that recent periods often provide a better indicator of the future, hence are given higher weights. In instances where the data exhibit seasonality, the selection of weight should also reflect these characteristics to ensure an accurate forecast. We now delve into the topic of forecasting errors, a key concept used in refining and selecting superior forecasting models. A forecast error is defined as the difference between the forecasted value and the actual outcome. It is important to note that all forecasts inevitably embody some level of error. The sources of these errors primarily stem from two aspects: bias, which is a persistent mistake made throughout the forecast, and random errors, which are discrepancies not captured or explained by the model being used. To evaluate and quantify these errors, we utilize measures such as mean absolute deviation, MAD, mean absolute percent error, MAPE, and the tracking signal. The MAD offers an average of the absolute errors. MAPE provides a relative measure of error, and the tracking signal detects any bias in the forecast error over time. By understanding and scrutinizing these errors, we can improve the precision of our forecasting models, making them more effective for future predictions. Forecast error measurements are essential tools to evaluate the accuracy of forecasting models. The mean absolute deviation, MAD, represents the average of absolute errors. Ideally, we want the MAD to be 0, indicating no forecasting error. Large values of MAD imply a less accurate model. The formula for MAD is the sum from I equals 1 to n of the absolute value of A sub t minus F sub t, all divided by n. where A sub t is the actual demand during period t, F sub t is the forecasted demand, and N is the total number of periods. The mean absolute percent error, MAPE, scales the forecast error relative to the magnitude of demand, calculated as MAPE equals MAD divided by average demand. It gives us a standardized measure of error, useful when comparing forecasts of different scales. The tracking signal, TS, is a measure that indicates whether forecast errors are accumulating over time, either in the positive or negative direction. It is given by TS equals running sum of forecasting errors divided by average mean absolute deviation. The tracking signal can provide a clear sign if there's consistent bias in the forecast. These measures collectively offers a comprehensive view of the forecast accuracy and reliability. We will now illustrate how to compute forecast error using a dataset consistent of 6 data points, each representing actual demand and corresponding demand forecast. The process begins by calculating the deviation for each data point, obtained by subtracting the forecasted demand from the actual value. This deviation represents the error for each forecast. Next, we compute the running sum of forecast errors, RSFE, which is the cumulative sum of these deviations. To calculate the mean absolute deviation, MAD, we take the average of the absolute values of these deviations, providing us with an average measure of forecast error. Given that the average demand is 1036.7, the value of MAPE is given by 66.7 divided by 1036.7 equals to 6.43%. The tracking signal, TS, is then calculated by dividing the RSFE by the MAD. The resulting TS can be used to detect bias in the forecast over time, helping us to understand and improve the accuracy of our forecast model.